So remember, we are investigating the topic of root locus, and today we are going to continue with it. We are going to see how to find the details on a root locus. So let us look at an example. So suppose that I have a system given like this. Let us say example here. So we would like to draw the root locus first, and then we would like to calculate some details on that root locus. So here, let us look at the open loop poles. See here, the open loop transfer function is k over s plus 1 and s plus 2. And I can write this as k times n of s over d of s. And here we see that n of s is equal to 1, which is going to determine the open loop zeros. And d of s is s plus 1 and s plus 2. Okay? So this actually means that I have no open loop zeros. And we have 3 open loop poles. Okay? And these open loop poles are at the origin, at -1, and at -2. Okay? So now if I place these on the complex plane, we have these open loop poles at -2, -1, and -2 here. Okay? So now the first thing that I'm going to determine is the root locus on the real axis. So when I look at a point on the real axis, a point on the real axis is in the root locus if and only if the total number of open loop poles and zeros to its right is an odd number. Okay? So here I see that. Do you think any such point here would be included in the root locus? No. What about this interval? It is going to satisfy the criterion, and that actually means that this interval is included. This one is not, and this one is going to be included. Okay? So as soon as I place the real axis parts, I can put some arrows onto the root locus so that the trajectories get away from the open loop poles and get towards the open loop zeros. Okay? So I can here place some arrows getting away from the open loop poles only. So here, in this case, how many asymptotes do you expect? How many asymptotes? So here, if we call this number n as the number of open loop zeros, okay, and n as the number of, this is open loop poles, m here in this case is 0 and n is 3. Okay? So how many how many asymptotes do you expect? We are going to have 3 asymptotes. So remember, trajectories start from the open loop poles and they go. So here remember the following equation. So if I have that equation, the closed loop poles are determined by the following equation, n of s over d of s. Okay, so this is equal to 0. We are always trying to solve this equation, and this equation can be written as 1 over n of s over d of s is equal to -1. Okay? And here I can write the following. K, n of s is 1 here, and d of s is s plus 1 and s plus 2. I'm trying to satisfy this equation. And start of the root locus means that k is equal to 0. If k is equal to 0, what should be this ratio so that the result of the multiplication is -1? Infinity. That actually means that s should be either 0, -1, or -2. Okay? So, and when k goes to infinity, if k is infinite, what should be this number so that the result is -1? This should be 0. When is this number 0? That actually means that this number is only 0 when s goes to infinity. Okay? And that actually means that the 3 trajectories are going to start from the open loop poles and since there are no open loop zeros, S is going to go to infinity, so that I have infinity times 0 is equal to -1. Okay? So that actually means that in this case I have 3 asymptotes that I can calculate. So here we have found the formulas for the angle of the asymptotes. Angle of the first asymptote is found by the formula 180 divided by n minus m. Okay? And we see that since we have 3 asymptotes in this case, the angle of the asymptote is going to be first asymptote is going to be 60 degrees. The angle between asymptotes is always twice this number. Okay? And it is going to be 120 degrees in this case. And we have also seen that there is a formula for the intersection points of the asymptotes. It is the summation of the poles minus summation of the zeros divided by n minus m. And in this case, summation of the open loop poles is -3. Summation of the open loop zeros, there are none. So I have 0 here, divided by 3. We see that the asymptotes meet at the point -1. Okay? And that actually means that I have my first asymptote with 60 degree angle. The second one is going to be 120 degree apart from this. And it's going to be pointing in that direction. And the third asymptote is going to be somewhere like this. And we see that one of the closed loop poles is already diverging away on the asymptote. And the other poles, they're going to meet at a single point. And then they're going to go complex, and they're going to try to follow these asymptotes here. Okay? So they're going to diverge to infinity. So in this formula, when k is infinite, this is going to be 0. We know that to satisfy this equation. These s's are going to go to infinity to satisfy this equation when k is infinite. Okay? So here, this is my root locus, and in this root locus there are some important points. For example, I can ask you how the settling time of the system is behaving for this system. Okay? So I can actually try to draw the settling time of the system, Ts, with respect to k. By the way, if I forget about the attendance, please tell me. So here, if I would like to draw the settling time of the system with respect to k, how can I draw it? Here, k is equal to 0. At k is equal to 0, what is the settling time? At k is equal to 0, we have a closed loop pole at origin. Okay? That actually means that the settling time is infinite. So we are going to start at infinity, and then the settling time is going to get smaller and smaller because the smallest closed loop pole to the imaginary axis is getting further away from the imaginary axis as k is increasing. That means that settling time is going to get smaller and smaller until which point? This intersection, this point is called the breakaway point for the closed loop poles. Okay, so here there is going to be a specific k value, which is k1, at which the two closed loop poles would reach that value. Afterwards, what's going to happen? If I increase k further, what is going to happen? Then the closest poles to the imaginary axis will start getting closer to the imaginary axis. Okay? And that means that the settling time is going to start increasing again. And they're going to increase forever like this. Here, at this point, there is going to be a specific k value. It is the point k2. Okay? At this k2 value, what is going to happen? When k reaches k2, what happens to the settling time? It will not settle anymore, so that actually means that the settling time will go to infinity there again. Okay? So that actually means that when I look at this root locus, I have to be informed about these k1 and k2 values. Or I can ask you the following question. For which k values does the step response of this system, does the step response of the closed loop system show no oscillations at all? So for which k values does the step response of the system show no oscillations at all? For which k values? From 0 to what? K1 here, okay? So we know that oscillations are caused by complex poles, okay? Complex closed loop poles. That actually means that if all closed loop poles are real, then there will not be any oscillations in my step response. That actually means that as I increase k from 0 to k1, no oscillations will be observed in the step response. Only after I increase the k value above k1 will we start to have actually oscillations with these dominant closed loop poles here. Okay? So that actually means that this k1 is really an important value. Okay? So here is the time at which the system has smallest settling time, or I can actually talk about the fact that it is the k value at which there will start to be oscillations in the step response of the system. So such points are called breakaway points in the root locus terminology. Okay? Roots break away into the complex domain. They start to have non-zero imaginary parts. Sometimes we have a break-in point as well. So I can give you a very simple root locus as an example. Let us say I have two open loop poles here and one open loop 0 here. In that case, if I look at the root locus, the real axis will look like this. And in this case, as soon as I place the real axis points, then I'm going to place also arrows, getting away from the closed loop poles, going towards the open loop zeros. Okay? How many asymptotes are there? There is the answer 2. Is it correct? How many asymptotes do I expect? Don't be shy. Tell me what the number is.
How many poles are there?
2.
Oh, right, 1.
There is only one asymptote. It is n minus n. N is 2, and n is 1 here. So there is only one asymptote. What is going to be the angle of that asymptote? 180, according to that formula. So that asymptote is looking like this. That means that one of the closed loop poles is going to diverge away to infinity on that asymptote. Okay? And then I'm going to complete this root locus like this. So here I see that there are two closed loop poles for each k value, and the k value, as I increase the k value, the two roots are going to meet here, and one of them is going to converge to the 0, and the other one is going to diverge to infinity. So here I see that. So here, what happens if I do the same thing here? If I try to draw the settling time with respect to k, okay? So let me give some values here. Let me say this is k1. Let us say this is k2, and let us say this is k3. Okay? If I would like to draw the settling time of the system with respect to k, how should the figure look like? So first of all, the closed loop system is unstable until which k value? Until k2, settling time is going to be undefined or infinite. I won't have any settling time. So the settling time is going to be finite after we pass the point k2 here. And the settling time is going to start from infinity, and it's going to get smaller and smaller when the closed loop poles are going in that way. Okay? And then at point k3, we're going to reach a minimum. Okay? We're going to come to here, and then after the point k3, one of the closed loop poles is going to start approaching the imaginary axis. That is the dominant closed loop pole, meaning that this settling time is going to start increasing from that point on. Is it going to increase forever? where is it going to stop at a finite value? Yes, so here, as I increase k, I see that the closest pole to the imaginary axis is going to stop here, and then that actually means that the figure is going to be something like this. Okay, so the settling time is going to settle at some point here. And here I see that this critical point, K3, is called a break-in point. Okay? And this is a breakaway point. Okay? So here, in the remaining part of this lecture, we are going to look at how to actually calculate these breakaway and break-in points. Yes?
How could you answer the question for that figure? At which value of k would our second order approximation be valid?
In this case, I can answer your question quite easily because so for this example, okay, that's better. Because here, answering it here, the system is already second order. So here, in general, we have a dominant pole approximation, as you might remember. Okay, in this course, we are accepting the dominant pole approximation to be valid if we have something like this, for example. Okay, if this distance is d1, okay, and if this distance is d2, in this course, we are accepting that the dominant pole approximation is acceptable if d2 is larger than or equal to 3d1. Okay, so that is our assumption in this course. And here I'm not sure. At this point, we are going to be able to calculate this point, for example, and it's going to be something very close to 0.5. Okay, so at this point, probably initially it will not be valid. The dominant pole approximation will not be valid initially. Okay, because if k is very small, I know that one of the closed loop poles is very close to -1, and the other one is very close to -2. So the ratio of the distances is around 2 initially. Okay, only when we increase k further, the approximation becomes better and better, and at some point it's going to be acceptable after some point. But for that specific value, calculating it probably it's going to be much more difficult than talking about it.
Hocam sağdaki teknik grafikte de aynı şekilde birim dominant olduğu yani kayıt
In the case of yes, in this case, you should investigate this figure quite like this. So at each k value, there are two closed loop poles. Okay, so that actually means that as I increase k, these two closed loop poles would approach each other and come on top of each other. And here, for example, if these two closed loop poles comes here, there is no dominant pole approximation in this case because there are only two closed loop poles actually here, and when I try to calculate the settling time there is no closed loop pole, there is no dominant pole approximation there. But when the closed loop poles come here and here, okay, in this case, of course, I'm making a dominant pole approximation, okay, and here I'm assuming that this is dominant. Okay, and this is not dominant, and the quality of that approximation depends on the ratio of the distances. Okay, if these are very close, of course, again that approximation, the validity of that approximation will be questioned. Yes, exactly. So there is a significant approximation here. Okay. Any other questions? Yes. Let us do it. So here, the question is, what happens if there is an S square here? Is the question? Okay. So I have double poles here. Okay. Then I have another pole here and another pole here at -1 and -2. In this case, we see that if I fill in the real axis first, I see that here there will not be any real point included in the root locus. Here, what about here? The total number of open loop poles to the right should be odd, or poles or zeros to the right should be odd. And here this number is again an even number, because the total number of open loop poles and zeros to the right is 2 in this case. It is an even number, so this interval will not be included either. But this interval now will start to be included. Okay? And there are no other real parts included in the root locus. Now I'm putting my arrows, getting away from the open loop poles, going towards the open loop zeros. So now I have to look at the asymptotes. So how many asymptotes do I expect? Yes? 4. There are 4 asymptotes in this case, and the angle of the first asymptote is going to be 45 degrees. Angle between the asymptotes will be twice that, 90 degrees. Where do the asymptotes meet? The summation of the poles is -3, minus the summation of the zeros, which is 0, divided by the number of asymptotes. The asymptotes meet at the point -3/4. That actually means that the asymptotes meet here. The first asymptote has 45 degree angle. And I know that the second asymptote is going to be 90 degrees apart from it. So we are going to have an asymptote like this, and an asymptote like this, and an asymptote like this. Okay? And now what am I going to do? These two closed loop poles, they're going to start here, and then they're going to go to their respective asymptotes like this. And what about these two closed loop poles? They're going to start from here. And then they're going to go to the asymptotes. Here you have to be very, very careful. This is quite a tricky root locus. And you have to check here what happens. For example, if these two closed loop poles, they might also go to the asymptotes like this. Okay? Alright? So you won't know. How can you check whether this is the case or not?
Stability condition.
Yes, if you check the stability condition, for example, if the system is unstable starting from 0, K0, if the closed loop system is unstable starting from just 0, what can you say? Then there won't be any intersections like that. The roots are going to go to the asymptotes like this. But if there is a stability range between 0 and 1, for example, then you would know that in that case the roots first will enter the left half plane first, and then they're going to pass into the right half plane. Okay, so again, that is going to be a point like this, intersection with the imaginary axis. Okay, so in this 2-hour lecture, we are going to first look at the breakaway points, how to calculate them, and then we are going to concentrate on the imaginary axis crossings. In imaginary axis crossings, there will be 2 methods to calculate those imaginary axis crossings. One of them is going to be just, I will find the characteristic equation of the system. I will find the characteristic equation of the system, and I will substitute S equals to j omega in order to be able to find the intersection with the imaginary axis. The second method to calculate the imaginary axis intersections would be using the route stability criteria. Okay? Because we know that if there is such an intersection, if there are 2 closed loop poles like this on the imaginary axis, what type of difficulty I'm expecting in route stability criteria? Difficulty 2. So that actually means that in order to be able to calculate such imaginary axis crossings, I can enforce difficulty 2 in my route array. Okay? And enforcing that difficulty will give us at which k values we are going to have imaginary axis crossings. Okay? That is what we are going to do in this lecture. So here, let us concentrate on the breakaway points or break-in points. Okay? So here, what is going to be important for us is that at a breakaway or break-in point, we are going to have double poles at a single location. Okay? We know that the characteristic polynomial of the system has double poles at a single location. That actually means that this is my characteristic equation in general. So it's going to give me the following characteristic polynomial. D of s plus kn of s is equal to 0. This is the characteristic polynomial for which we are drawing the roots in our root locus plots. Okay? So that actually means that if I call this as the characteristic polynomial C of s, then that actually means that at a breakaway or break-in point, there will be roots with multiplicity 2. Okay? So I will have the characteristic polynomial looking like this at a breakaway or break-in point. Okay? So this characteristic polynomial should have double roots at a single location for a breakaway point or break-in point to exist. Okay? So that actually means that my characteristic polynomial is something like s minus m squared times another polynomial here, which I call as p of s. So then the question is, how can I find what this m is and what is the k at that m value? I'm going after these two numbers, m and k. The first thing that I can do is that if there are double roots at that point, that means that this polynomial is going to have a root at that point. So that actually means that I have d of m plus k n of m is equal to 0. Okay? This equation should be satisfied trivially, okay? Because c of s, this polynomial, is equal to this one. That actually means that if I substitute s equals to m, then I need to satisfy this equation. Yes?
But for that specific k, right?
For that specific k, exactly. For that specific k, I need to satisfy this equation. And my aim is to find both m and that specific k value. Okay? So here, this equation unfortunately will not be sufficient for us to locate m and k here. There are two quantities here that I'm trying to obtain, but there is only one equation. So here, what more can I say about this m? So I need one more equation to be able to locate this m and k. How can I find that equation? So here, an interesting thing is that I know the structure of this C of s. Let us look at the structure of C prime of s. C prime of s is the derivative of the polynomial c with respect to s. Okay? If I look at its derivative, the derivative can be calculated as derivative of the first term. It is 2s minus m times p of s, the second term, plus the first term times the derivative of the second one, s minus m squared times p prime of s. Okay? So this is the derivative of c prime of s at that specific k value. Okay? So here, what happens if I substitute s equals to m in this equation? The right hand side is again going to be equal to 0. C prime of m should be equal to 0 as well. So that actually means that if a polynomial has double roots at a single point, then the derivative of that polynomial has also the same root. Okay? So if a polynomial has double roots at a single point, then the derivative of that polynomial should also have the same root at that point. It can be a single root after that point. The derivative might have a single root, but it is going to have a root anyway. Okay? So that actually means that I can actually take the derivative of this polynomial, and the derivative should still satisfy the same equation. Okay? If I calculate c prime of s, it is going to be d prime of s plus k n prime of s. Okay? This k is independent of s now. So that, and I can substitute here s equals to m, which is going to give me the following: d prime of m plus k n prime of m is equal to 0. Okay? So this is my first equation to locate k and m, and this is the second equation locate K and M. Okay? And now using these equations, I can actually try to solve for these numbers. So the first thing that I'm going to do is that I will try to solve for M. And in order to be able to solve for M, I'm going to cancel K from these equations. From both of these equations, I can try to solve for K. And I can actually write this as K is equal to minus dm over nm. Okay? And I'm assuming that n of m is not equal to 0. And for the second equation, I can do the same. Minus d prime of m divided by n prime of m. Okay? And here, this is the second equation. And I can equate these two results together to write the following equation. D of m and n of m is equal to d prime of m, n of m, n prime of m. Okay? So we get this thing, and I can write this equation as follows. N prime of m, d of m, minus d prime of m, n of m is equal to 0. Okay? This is the equation characterizing the breakaway or break-in points. So if I can calculate here the following polynomial. If I can calculate the polynomial m prime of s, d of s, minus d prime of s, n of s is equal to 0, I know that my breakaway or break-in points will be a root of this polynomial. Okay? So this is a polynomial, this is going to be again a polynomial, and I know that the roots of this polynomial will give me my breakaway or break-in points. And after finding these roots, how can I calculate the k values corresponding to those roots? Substitute it in one of the equations. Okay, so you can just substitute it in one of the equations here. So after finding the breakaway break-in point candidates here, you can find the corresponding k values by substituting those roots into one of those equations, and the result is going to be the same for both equations. So whichever one is easier for you, you can make that substitution and calculate this. So now let us come back. So here sometimes people would actually try to write this equation in the following way. So here I know that this equation would always be satisfied in a root locus plot. Okay? So this equation is always satisfied. That means that we can write k is equal to minus d of s over n of s. Okay? Just to characterize this equation, people would write the following equation. They would write d over ds times k is equal to 0. Okay? Do not try to extract a meaning from this equation. Okay? Because here k is a parameter independent of s here. Okay? They are only dependent through this equation here. And I can actually write this equation as follows. K is given like this. Okay? K is given like this to us, and if I take the derivative of the right-hand side, I'm going to get exactly the same equation as this one. Okay? Let us try to do that. So the derivative of the right-hand side here, with respect to s, would be the following. Derivative of the first term, I have d prime times the second term minus derivative of the second term, n prime times d divided by n squared is going to be equal to 0. Okay? But we see that here, if I write this equation, then the numerator should be equal to 0, because the overall ratio is 0, then the numerator is 0, but the numerator is being equal to 0 is exactly equivalent to this equation. Okay? So sometimes instead of writing this equation, people would write just this equation. Okay? But that is exactly the same thing. So now let us try to go back to this example and let us try to calculate this breakaway point in this example. Okay? For that purpose, I have my n and d given like this. N is 1 here, and d is I have s cubed plus 3s squared plus 2s. Okay? So now if I try to apply that formula, what is n prime of s? Derivative of n of s, which is 1 with respect to s. It is 0, so I won't have the first term. 0 times d of s, and I have minus d prime of s. It is 3s squared plus 6s plus 2 times n of s, which is 1, should be equal to 0. Okay? And that actually means that we have s squared plus 6s plus 2 is equal to 0. And if you try to find the roots of this polynomial, you're going to find the following numbers. So the roots in this case are at minus 1 plus minus 1 over square root 3. Okay? So, and if you look at these roots, they are going to be looking like the decimal representation would be minus 1.57 and minus 0.42 here. Which one is my breakaway point? So by looking at this root locus, usually you would locate which one you are interested in. Okay? We're going to be interested in of course this one. Okay? That is going to be minus 0.42 is going to be my breakaway point. Then what about this thing? What is this? So here, remember, by using this, you can actually calculate what the k values for each of these roots would be. Okay? And you can actually calculate k values using either of the methods. Either k is equal to minus d of s over n of s, or k is equal to minus d prime of s divided by n prime of s. Okay? So here, if you, in this case, actually n prime of s is equal to 0 in this case. Okay? So this formula the second formula is not really applicable in that case, because n prime is equal to 0. That actually means that I need to use this formula instead. Okay? So I will actually calculate k is equal to minus s cubed plus 3s squared plus 2s divided by n, which is 1, and I will evaluate this at the s value, minus 0.42, or at s value, minus 1.57. Okay? If you make these evaluations, you would calculate the following k values. The first k value for the first number is going to be 0.38, and for the second value, I will have minus 0.38. Okay? We are always drawing our root locuses for 0 or positive k values. Okay? This actually means that the second point that I have located here is for a negative k value. For a negative k value, there are double roots at some point on the root locus. In this course, we don't see the root locus for negative k values. It is actually called complementary root locus in control theory. We can actually draw a root locus for negative k values as well. Okay? And it is called complementary root locus. And it is going to be looking like something like this. So if I have 3 roots here, in complementary root locus, the angle condition changes. Now, in this case, these points would start being included into the root locus, okay? But these points would start being included. And then the asymptotes would also check. You are not responsible from anything that I draw here. This is a complementary root locus, which is not included in 302, okay? So this is a root locus for negative k values, okay? So I can actually draw something like this. This is my root locus for negative k values. There will be some asymptotes here. again, but they are going to be looking like this because the angle condition has to be changed for negative k values. Okay? And here, where is the k value minus 0.38 in this complementary root locus? Right here. Okay? So at this, so the roots start again from the open loop poles at k is equal to 0, and now I'm decreasing k into the negative values. And at this point, at k is equal to minus 0.38, there are again a breakaway point for which we can obtain by using the same formula. So here, if you obtain multiple points, then in order to be able to extract the breakaway point that we are interested in, you can just look at the k values and you can neglect the negative k valued quantities, s values, okay? And this thing is going to be what you're going to be interested in. Now I can ask you the following question. For which k values does this closed loop system have no oscillations in its step response? For which k values does this closed loop system have no oscillations in its step response? Between 0 and 0.38. Okay, that has to be your answer. Any questions here? Yes.
Do we have always symmetric k values at the end of the calculation time?
No, that was this. I calculated this last night, and it surprised me. If I did not make any mistake, these were symmetric somehow, but that is not the case. Yeah. Yes, coincidence in this case. So here, so sometimes you can actually have some polynomials. Unfortunately, the roots might not be found analytically. Okay. So remember, for example, the following example that we have considered. I have roots here, and I have some roots here. Sometimes, if you calculate this polynomial n prime times d minus d prime times n, you might need to use a computer in order to be able to find that roots, because usually this polynomial would have really a high degree, and the only possibility for finding those roots would be just to use a computer. Okay, so unfortunately, this type of calculation is not always possible analytically. You might need to resort to a numerical computational tool in order to be able to find those roots.
K negatif olduğu zaman sistemin stabilitesiyle ilgili direkt şey değiştirdi. Yani sabit görünmeye göre bir şekilde stabil olmuyor.
In this case, yes. So when you look at this complementary root locus, in that case, I see that there is always a root, there is always a closed loop pole in the right half plane. That actually means that for no negative k values will this system be actually stable.
Bu okulun transformation negatif olmasıyla ilgili bir şey.
No, so sometimes there might be systems. So here you can actually look at the following root locus. Suppose that my open loop, for example, this one, okay? So we see that here for some small k values, the closed loop system is unstable. For large k values, closed loop system would be stable. So actually, most of the times, if you draw the complementary root locus, because of this, so here let us try to draw the complementary root locus for this one, for example. So I can actually try to look at this thing. This is not going to work probably. So let me. No, I have to, for negative k values, it's usually more difficult to stabilize a system. Okay, but this really does not mean that for all negative values, the closed loop system will be unstable all the time. Okay, for example, you can try to look at this root locus, for example. So I can have this part is I'm drawing the again complementary root locus. So you shouldn't consider yourself to understand why these are like this. So I'm trying to draw the complementary root locus here for negative k values, and I'm going to fill in these intervals now. Okay? So in that case, I see that the root locus is looking like this. This is again a complementary root locus. We see that for some negative k values, the closed loop system is still stable. Okay? So really, we might sometimes have systems with negative k values which might become stable. Okay? But of course, if I increase k and magnitude of k for some large values, of course, there will be some unstable region. But still, for some negative values, we can have stability. Any other questions? Okay, so here we have found the breakaway and break-in points. So now we are going to consider imaginary axis crossings. Imaginary axis crossings. If I ask you in this example, if I ask you what is the stability range for k, by looking at this root locus, what can you tell me? So I have k2 value here, k1 value here. If I try to find the stability range for the system, what should I write? What should be this? K2. Do you think I should have equality here? I cannot have equality because at K2 we have two closed loop poles on the imaginary axis, and we never include imaginary axis in our stability region. Okay, and I can write here just 0. So for determining the range of k for stability, we need this K2 value with this intersection. Okay, at this point, we say that the system has sustained oscillations, or you can actually say that at this point, the closed loop system is undamped. Okay, you can actually say it. It's approximately second order and undamped. If I have K2, if K reaches this value, I would know that the closed loop system step response will show sustained oscillations. Oscillations which are neither growing nor decaying. Okay? And these are at this point, the closed loop system is still unstable, and we would like to be able to find those points. There are two methods here, as I told you. The first method is to substitution of s equals to j omega in d of s plus k n of s is equal to 0. We are going to do this substitution, and we are going to solve for omega and k. This is the first method. And the second method is going to be Rao-Hurwitz stability criterion. And an application of the Rao-Hurwitz stability criterion is going to use one of the difficulties. We know that if we have closed loop poles at these points, then that means that if at that k value, if I apply the route stability criterion, I need to encounter the second type of difficulty. Okay? And that actually means that in order to be able to locate such a point, I can apply route stability criterion to my characteristic polynomial, and I can enforce a second type of difficulty. And I can find the k value for which we are going to encounter such a difficulty. Okay? And that is going to be our second method. But before that, we have our break. Let us give a break. We can start at 42 past 4. 42 geçe tekrar başlayabiliriz. Merhaba. Kusura bakmayın, sizi böyle tam tatilden gelir gelmez şey yaptık. Kusura bakmayın gerçekten. Böyle. Öğrenci